Hi everybody, today's video is going to be on a synchronous reluctance motor. So this will be similar to a synchronous permanent magnet motor, but the rotor doesn't actually have any permanent magnets. It uses what are called flux guides and flux barriers. So these air gaps are flux barriers and these iron slots are flux guides. And first, I'm going to have you guys go to the canvas and download these two files. The first one that I was just in is the Sync RM36 slot 4 pole geometry. And then go ahead and download this Excel worksheet, but we're not going to use that immediately, but you can go ahead and download it right now. So what we're going to start off doing in Ansys is we're basically going to be defining all the excitations and creating a bunch of variables so that we can calculate the peak torque angle like we did with the permanent magnet motor. But this time we're going to go a step further and we're going to calculate, or we're going to extrapolate the torque speed curve of this motor by also analyzing the back EMF that's created at different speeds. So let's just start off. I'm going to start off by just creating some windings. So I'm going to create 3 phases, U, V, and W. And make sure you select stranded. So now we have these 3 phases, and I'm going to go ahead and make variables for them. So I'm going to say the current in U is just called U. Hit OK. Current in V will be called V. Current in W will be called W. And then if we right-click Maxwell 2D Design, then click Design Properties, we can see these variables. So the next thing I'm going to do is write the current excitations that will be applied to these phases. So for U, I'm going to create a variable called var cur. That's going to basically be the peak current of the waveform, the 3-phase current, and then times cosine, and then in parentheses 2 times pi times elec freq, which is that's gonna create another variable for the electric frequency, times time, and then let's say plus delta times pi over 180, and hit enter. I'm gonna say OK for all these variables. And then I'm just gonna hit Control C and Control V and copy paste these into the U, V, and W phases. And then I'm gonna edit V and W to be shifted 120 degrees apart. So I'm gonna say plus 2 times pi over 3. And then for this one, I'm gonna say minus 2 times pi over 3. Apply. I'm going to hit OK and save real quick. So again, if I right-click Maxwell 2D Design and then click Design Properties, it'll show me my variables. So I'm going to click on U and hit Edit. And then Unit Type, I'm going to find Current. I'm going to set it to amps. I'm going to do the same for V and W. Hit OK, apply. And now I'm going to decide what the peak current is by basically deciding what my current density will be. So I'm going to save this, and I'm going to click Measure Object. And right now, I have all these windings as one solid object. And this was a question in class before, I think. And I think it is useful to unite all these slots so that it can just be one excitation, because I remember before for one of the examples we had to click each of these slots and then assign them to a phase. So instead, here I'm gonna select this and edit Boolean separate bodies. So now these are separate bodies, and before we would just have to select this and then click assign coil, right? And do it for each of these little slots. So what you can actually do is select all of these, and all of these slots are going to be facing, their current is going to be flowing in the same direction. Excuse me. So all of these slots have the current facing the same direction. So I'm going to right click, edit, Boolean unite. So now they're one object. And I basically did that for you guys already with the geometry with all the other phases and the different directions the phase currents flow. So, however, now we're going to have to consider how many turns these 6 slots have. So basically, I'm going to click Measure Object. I'm going to click these 6 slots. So the area is about 693 millimeters squared. So I'm going to use the calculator. So I have 693 millimeters squared, and there's 6 slots, so I'm going to divide that by 6. So this is the area of the windings in one slot, and I'm going to say that there is 10 amps per millimeter squared per turn, so in one winding. So I'm going to multiply this by 10 amps, and that'll be 1,155 amps flowing through the entire slot. So then if I want, this is all in RMS currents, so if I want the current to be 100 amps RMS in one wire or one turn, I'm going to divide this by 100, and then I'll get, this is how many turns per slot there will be. So I'm just going to round it down to 11. That'll increase the current density a little bit. So now I've found out that we have 11 turns per slot, and in this one object we have 6 slots. So I'm going to multiply this by 6, and now for this one object, when we assign the excitation, we're going to make the number of turns 66. So I selected U1. Now I'm right clicking U, assign coil, and I'm going to call this U1 in. So these sets of windings should be pointing into the screen. So I'm going to make that negative, and then I'm going to write turns for the number of conductors. And I'm going to hit OK. I'm going to say the value is 66 turns, which we just calculated. And I'm going to check the design properties. So yeah, 66 turns. And I'm going to edit these other variables actually to be no unit type. And like I said before, the peak or the RMS current is going to be 100 amps. So that'll be square root of 2 times 100 will be the peak. So I'm just going to write, for varchar, I'll say 141. And for the frequency, for now, I'm just going to write 100. And for delta, I'm going to leave it at 0 for now. Hit apply. and hit OK, save. And I'm going to go back to design properties, and I'm going to add another variable. I'm going to make the variable for the RPM, and that's just going to be the electric frequency times 120 over 4 because there's 4 poles. And then unit type, angular speed, RPM. Hit OK. Save that. So now I'm going to go ahead and assign the rest of these windings. So U2, I'm going to right click U, assign coil. U2 is going to be facing out, so polarity positive. And then I'm going to write turns for the number of conductors. I'm going to copy this so that I can paste it in the other ones. And then V1, assign coil. V1 is going to be out, so positive, and then number of conductors will be turns. V2, assign coil. V2 will be in, negative, number of conductors turns. W1, assign coil. W1 will be in, number of conductors turns, so negative. Make sure that's negative. So, and then W2, assign coil. W2 will be out, so polarity positive. Save that. And now we should have our winding set up. Out positive, in negative, out positive, in negative, and all their turns are 66. Looks good. Next, I'm going to go to select object edge. I'm going to select the outer region edge. 1 second. There we go. I'm going to right click boundaries, assign vector potential value 0. Okay. Save that. Excuse me. Then I'm going to select the band. I'm going to go back to select objects, select the band, right click model, motion setup, assign band, motion type, make sure it's rotation, mechanical, and then the angular velocity will be the variable RPM that we made. Save that. Now I'm going to select all the iron components, and you guys already know how to import this material because we did it in previous videos and lessons. And so I'm selecting all the iron. I'm going to right click mesh, assign mesh operations on selection, length based, and I'm going to make it 6 millimeters. I'll call this iron. And then I'm going to select all the copper, right click mesh, assign mesh operation on selection, length based. I'm going to make this 3 millimeters. Call this copper. Save that. And I'm going to make another variable. So I'm going to right click Maxwell 2D design, click design properties, and I'm going to add another variable. Call this one elect cycle. Hit OK. And then I'm going to make this 1 over the electric frequency. So that's basically the electric period, or 1 cycle. And I'm going to edit this so that it is of the unit time and make sure it's seconds. Okay, apply. So UV and W are all in amps. RPM is in RPM. 1 electrical cycle is in seconds. Excuse me. And varchar, electfreak, delta, and turns can be left unitless. So, okay. Save. Now I'm going to create an analysis. So right click analysis, add solution step. Call this one elect cycle. I'm going to copy this and paste it for the stop time. Then for the time step, for now I'll do 50. Hit OK. Save. And so I'm going to create this optometric. So add parametric, add delta. And we've done this before where we sweep. So I'm going to sweep from 0 to 180 in step 10 for now. Add that. OK. OK. I'm going to rename this delta. And instead of actually simulating this for now, I'm just going to go ahead and tell you guys what the peak torque angle was from this optometric, from this parametric. So go ahead and right click Maxwell 2D Design, Design Properties, and then set delta as 30. So this should give you the peak torque angle, and this is what we're going to be simulating. So, okay. Now I'm going to make another parametric that we're actually going to use. So add parametric, add. This is going to be of the electric frequency. So I'm going to start it at 100 and stop it at 200 hertz and step it 100. So we're basically just doing two simulations, one at 100 hertz and one at 200 hertz. I'm going to rename this elect frequency, then back EMF. So I'm going to save that. And I believe this is an already made model. Let me just double check. Yeah, we've basically got everything set up. So yeah, I think we've got everything set. So I think now we can go ahead and import this to the web browser. So I already have some files in here that I was working on before. So I'm gonna upload the file we were just working on. So we were working on the Sync RM 36 slot 4-pole geometry. I'm gonna go full screen. Now I'm gonna go ahead and open that. And then double click Maxwell 2D design. This 3D design is basically the geometry I imported from SolidWorks. And now I'm going to go ahead and run the electfreak optometric. And this is going to take a long time. So I'm going to speed this up in post. Alright, now that it's finished, I'm going to right click results, create transient report, rectangular plot. And I'll plot the moving torque just to show you that it is really jumpy. And that's because it's a synchronous reluctance motor and not a synchronous permanent magnet motor. The poles on this motor kind of they're not very consistent because this is basically the pole face right here. Whereas the pole face with a permanent magnet machine would have, the magnets are like more well defined. The flux kind of, when this rotates, kind of just finds different ways, different paths, whereas with the magnet it's just always consistently rotating. So this, as long as it looks like this for you, as long as you have some sort of positive torque, you should be fine. So the next thing I'm going to do is I'm going to create transient report rectangular plot, and I'm going to do moving torque, mean moving torque versus the electric frequency. And it should be basically the same. And so make sure you have this spreadsheet that I put on Canvas open, and right now we can fill in this peak torque value. So from this simulation, if you right click on the plot area and click marker, add marker, we can see what the peak torque is. So yeah, it's basically the same number, just still barely slightly different at the two different frequencies. It should be the same at both frequencies. So our torque is about 228 Newton meters. So then if you go to the spreadsheet, that's what we can input for the peak torque. I'm going to write 228 Newton meters. And now we come back to the simulation that ran. And if I right click the plot area, I can end marker mode or hit escape. And next I'm going to right click results, create transient report rectangular plot, and then click winding, then click induced voltage, and then hold control and select U, V, and W, new report. And they're kind of overlapping each other, but basically this is the back EMF of both the simulations at 100 and 200 hertz. And you can see that the 200 hertz simulation is kind of squashed because since it was at a higher frequency, the period was over a shorter time, right? But what we're going to do with this is, maybe I can comment more, it's really ugly looking. It's not super smooth like an IPM motor. So to find out how the back EMF limits the max speed of the motor, or not the maximum speed, it's called the base speed at which the constant torque region ends, then we will have to take a FFT. So let me just search synchronous motor torque power speed curve. So for synchronous motors, this is the typical characteristic. So this is omega base, this is the base speed. So the torque stays constant until the base speed, and then this is the constant power region, and this is the flux weakening region, which is sort of advanced concept. But basically the torque stays constant until the base speed, and then you can do what's called flux weakening so that you can increase the speed further so that the back EMF doesn't limit the speed anymore, but then that's a trade-off with torque. And as you approach the base speed, the power output is increasing, and then when you reach the base speed, the motor can no longer output any higher power. So going back to this, how are we going to figure out the base speed? Basically, in this spreadsheet, we're going to find out the limiting voltage versus the frequency proportional to the rotor speed. So let's do this. I'm going to go full screen again. And if you right-click results, then you can go to, whoops, I think I got an email. You can go to perform FFT on report, and then click winding plot 1, and the window will be rectangular. And then make sure the function is magnitude. Hit OK. And now we have this FFT of the back EMF. So you can see there's a bunch of harmonics because obviously this plot isn't perfectly sinusoidal. And the harmonics we care about are at 100 Hertz and 200 Hertz. So we're going to use the marker again. So I'm going to right click the plot area, marker, add marker. And I'm going to see this is for 200 Hertz. This is for 100 Hertz. And whoops. And for 200 Hertz, the back EMF magnitude is 1000 volts. And at 100 Hertz, the magnitude is 515 volts. So 1032. So let's go over to the spreadsheet. So for electrical frequency 0, we can put 0. So we did 100 and 200. So then the rotor speed, I'm going to say equals electrical frequency times 120 over 4. Then I'm going to drag that down. And then the back EMF peak at 0, it's just going to be 0. And at 100, it was 515. 515. And then at 200 Hertz, it was 1032. 1032. And next, we're going to calculate the voltage drop across one phase. So a lot of this stuff is sort of three-phase inverter related, or mostly this battery peak supply. But so remember we did the area of one slot earlier that turned out to be 115.5 millimeters. Then if the slot area is, let me pull up the calculator again. So the slot area is 115.5. Then there's 11 wires per slot divided by 11. Then the wire area is going to be 10.5 millimeters squared. So I'm right, 10.5. And then the model depth was, let me check. Design settings, 150 millimeters. So let's look at the 3D model. Basically, right now I'm sort of guesstimating the resistance of a single phase of this motor. So you can imagine there's a bunch of windings looping around this thing. So there's going to be a length component relative to the length of this motor, and then there's also going to be another length component where you're going to have to bridge the wires here to the wires here to the wires here to the wires here. So the wire is wrapping around in out of the screen, and then across the screen to link over here, and it's wrapping around this, and it's wrapping around this, and it's going over here, and it's wrapping around this, and it's wrapping around this. So the model depth is going to be 150 millimeters. Then the phase bus, so the bus between slots in the phase, I'm just guessing is like 100 millimeters. The distance between here to here is like 100 millimeters. So it's just an estimation. Maybe be on the safe side, I'll say it's like 120 millimeters of wire that is going around this edge, not actually contributing to the slots. So I'll say 120 millimeters. So then the total length of one phase would be equal to the model depth, and each phase has 12 slots. So the model depth times 12 times, there's going to be 11 wires per slot, plus the phase bus guess times, I'm going to say 4. I'm going to say it bridges 1, 2, 3, 4. So this is just a guesstimate, times 4, or whoops, let me edit that, times 11 turns. Oh, and then the resistivity of copper, I think it's like 1.77 times 10 to the minus 8 or something. Resistivity of copper. 1.72. Okay. I'm going to say 1.72 times 10 to the minus 8 ohms per meter. 1.72 or equals 1.72 times 10 to the minus 8. And then I'm going to get the wire area in meters squared. So this is going to be this wire area in millimeters squared times 10 to the minus 6. And the phase length in meters is going to be equal to the length in millimeters times 10 to the minus 3. And the resistance of one phase, this is a pretty rough approximation, will be equal to the resistivity times the length in meters divided by the area in meters squared. So it's only about 0.04 ohms. So then the current is going to be, we have 141 amps peak as the current, and the current RMS is going to be 100 amps RMS. So the phase drop, the peak drop, is going to be equal to the peak current times the resistance of one phase, and that's going to be about 5.8 volts. Let me check what I got for this other simulation. Actually, this was a different simulation, so pretty similar though. Alright, so the I phase times R peak drop, I'm going to say is 5.8 volts, and I'm going to drag that down. So then I'm going to make the back EMF plus the peak will be back EMF plus peak, and now we're going to write the back EMF, or the phase voltage drop is pretty negligent for this motor actually, mostly because the current we're running it at isn't super high. I mean, 100 amps RMS is really high, but it's not super high in terms of electric vehicle motors, I guess, is the relativity I'm speaking about. But anyways, so for the max supply of a 400 volt battery, that's going to be equal to 400 times 2 divided by pi, and then so 400 times 2 divided by pi, and that's basically going to be an artifact of the way an inverter works in a three-phase motor, where Let me just search it up. Let's see. 3-phase inverter. Let's see, motor. So basically the way this 3-phase inverter works is this is the DC voltage of the battery, and these are voltage controlled switches, so they'll either be high power MOSFETs or typically electric vehicles use IGBTs, but basically turning on this switch would allow current to flow here, and it would flow positively through this first phase of the motor, and then if you turn on this switch and this switch, it'll flow out half and half through these two phases. And there's basically a bunch of combinations, not a bunch, like 8 combinations that you can put these switches in, and by switching between these combinations super fast, you can create a 3-phase supply on whatever motor source you have, right? So because of that, the max voltage a battery can supply to one phase of the motor is going to be equal to 400 times 2 divided by pi, and then we're going to multiply by 0.95, and this is what's called a modulation index, and that's sort of another thing related to inverters. It's basically like how much time in the PWM can you spend like turning it on like all the way. I don't know, it's kind of hard to explain. So it's going to be the battery supply times 2 divided by pi times the modulation index, which is 0.95. And 0.95 is actually a really high modulation index, but we're just going to go with it. So drag that down. And then for an 800 volt battery, I'm going to take this, Control C. It's basically going to be the same, except the battery is now 800 volts. Drag that down. And now we can plot, I'm going to save this. We can plot the rotor speed on the x-axis, and we can plot the back EMF on the y-axis, and then we can also plot the max supply on the y-axis. So I'm going to drag over rotor speed, and then I'm going to hold control. I'm going to select back EMF plus IR V peak, and then I'm going to go to insert, then I'm going to choose scatter with straight lines. So save that. And I'm going to put access titles and a legend, and I'm going to change the legend to be on the bottom. So if you click here, put it on the bottom. And I'm going to zoom out a little bit so I can make this bigger. I'm going to title this base speed calculation. And so this y-axis is going to be voltage, and this x-axis is going to be speed in RPM. And now if I right click this graph, I can click select data, and so I have series 1 selected. I'm going to edit it, and I'm going to title this back EMF plus IR. Hit OK. And I'm going to add, so I'm going to say this is 400 volt bat max supply. And then I'm going to click on X values. I'm going to drag over rotor speed. Now I'm going to delete this. Now I'm in Y values, and I'm going to drag over the 400 volt max supply. I'm going to hit OK. And I'm going to add another one. I'm going to say this is 800 volt bat max supply. And the X values, I'm going to drag over rotor speed, delete the Y values, and then I'm going to drag and hold, click over 800 volt bat max peak. Okay. I'm going to save this. So now you can see that the back EMF is linearly increasing as the speed increases. And at the points where the back EMF intersects these lines is where the base speed will be. So for an 800 volt battery, at this point where the back EMF intersects this flat line for the 800 volt battery, that will be the max speed with max torque that the battery and inverter can drive this motor. So I'm going to click here, and I'm going to add a trend line for that. And then I'm going to display equation on chart. And save. I'm going to pull up the calculator again. So let's create the torque speed curve. Next, we're going to create the torque speed curve for an 800 volt battery driving this synchronous reluctance motor. Excuse me. So the max supply is going to be 483.8 volts, which is going to be this Y value. So we're trying to find where this line intersects this 800 volt supply value. So that's going to be 483.8 volts. And then we're just going to do algebra. So minus 5.5 equals this divided by 0.172 equals 2,780. So at 800 volts, the base speed is going to be 2,780 RPM. And we can go ahead and calculate it for 400 volt battery. So 241.9 minus 5.5 divided by 0.172 is 1,300, we'll say 75. 1,375. I'm going to write RPM. Okay, so I'm going to save that. And now we basically have all the information we need to make the torque speed curve and the power speed curve similar to this image. So I'm going to go back to the Excel. And so the torque peak was 228 Newton meters. So first I'm going to go here to speed. I'm going to start this one at 0. Make this equals the one above it plus 100. I'm going to zoom out here. Drag this down. So let's go all the way to like 5,000 RPM. And then the torque is going to be 228 Newton meters. So 228. And from this characteristic, at the base speed, it will be constant up until the base speed. So (228 Newton meters), and the base speed for the 800 volt battery was 2,780. So I'm going to drag this. Oops, too far. 2,780. So I'm going to drag this to 2,800. It's close enough. And then after 2,800, this isn't exactly what the flux weakening region will be like, but what I'm going to do is a good approximation. So basically in the flux weakening region, it'll be this exponential decay and it'll be proportional to the speed. So I'm going to say this equals 228 times the base speed, so 2780 divided by 2,900. And then if we drag this down, it'll be an exponential decay as the speed increases. And the power of the motor will basically be the torque times the speed in radians per second. So this equals torque times speed, and this is an RPM, so it's going to be times 2 times pi divided by 60. And then I'm going to divide this by 1,000. So that's in kilowatts. Now I can drag this down. And now we can go ahead and create plots for the speed, or the torque versus speed, and the power versus speed. So I'm going to drag and select speed and torque right now. Insert. I'm going to say scatter with straight lines. Make this bigger. And I'm gonna wait to add axis titles. I'm gonna add a legend, then put it on the bottom. And now if I right click this chart, let me just make sure I'm still recording. Yep, all right. I'm gonna right click this chart, select data, and I'm gonna edit this one. So this series name is gonna be torque. And then I'm gonna add one, and I'm gonna call this power. And then the x values will be the speed. And then the y values will be the power. Hit OK. And hit OK. And then I'm going to right click this. And I'm going to go to change chart type. And I'm going to go to combo. And so for the torque, I'm going to keep it scatter with straight lines. And for the power, I'm going to make it XY scatter with straight lines. And I'm going to put the power on the secondary axis. Hit OK. And now I'm going to add a chart title and add axis titles. And I'm going to make this a little smaller actually. So I'm going to call this torque slash power versus speed. And then this is going to be the torque in Newton meters. This is going to be the speed in RPM. And this is going to be the power in kilowatts. And now we're basically done. Now we've got this torque versus speed curve, and just because I'm gonna format axis, make the maximum 5,000. Make sure I save this, and next I'm going to create another field density plot. So I'm not sure, did I have save fields on? Properties, save fields. Okay, so I'm not going to have you guys submit this, but I'll just show you. I'm going to delete all reports. And you can clean up solutions as well. That'll delete all your data. So I basically have a file with no simulation ran anymore. Let me say this first. So this torque / power versus speed curve and this base speed calculation is what I want you guys to submit to Canvas. So just go ahead and submit this file to Canvas. And that's what'll be the grade for the assignment. I haven't made the assignment yet, but it'll probably be called like Ansys assignment, synchronous reluctance motor, torque and power versus speed curve or something like that. So yeah, basically make sure you followed all the steps. You filled in the Excel sheet and you created the torque / power versus speed curve. And that's what you'll submit to Canvas. And hopefully I remember, and I'll reiterate this in class tomorrow on Friday. Oh, I just doxed the date I'm filming this. But yeah, so on Friday I'll basically tell you guys that you'll have to submit this as well. But I haven't made the assignment yet. So this is just for funsies. I'm going to go to 1LX cycle, properties, and I'm actually going to do save fields. And I'm going to do 100 steps. Save that. And now I'm just going to analyze this. And I'll cut this out in post. Alright, now it's done. So basically I wanted to turn on save fields so I could fields make a flux density animation like we did in the last video. So doing that right now. Double click there. 0 seconds. And right click animate. So yeah, I just wanted to plot this because it looks cool. And you can sort of tell that these flux guides have pretty high flux density in them, really. Like 2.5 Tesla is a lot. So this is a really big motor too. But I just wanted to make this animation because I thought it looked cool. And yeah, basically I'll reiterate, the only thing you have to submit for the assignment is the Excel sheet filled in with the base speed calculation and the torque versus speed plot and the power versus speed plot you calculated from your simulation. So yeah, thank you guys.